Okay, well, hello and welcome. This is Stats 13, and thank you guys for joining me, and it's really good to see you guys. And if you want, I'm not going to force anybody to do it, but if you want, I greatly appreciate you turning on your cameras. Thank you to everybody who has already turned on their camera. Of course, you are entitled to your own privacy and things like that. You don't have to turn on your camera, but for me, it makes a difference. I'm I'm a bit of an extrovert, so I feed off of just kind of the energy of other people, and if I only just see blank boxes, it's a little bit sad for me. But if you're just there and you just smile or you nod your head, or even if you shake your head, there's just a little bit of interaction. I feel like, oh, great. Okay. And then if you want to keep your cameras off, you can always interact using the reactions, right? You can give me whatever this confetti cannon is, or things like that, thumbs up and hearts. Yeah, there you go. So thanks, thank you for that. Okay, let's get started. Oh yes, welcome. That's section 1. That's very important. Okay. So this is me. My name is Miles Chen, and that's my email address. Although, to be honest, email is not the best method of communication for me. You can call me Miles, Professor Chen, Dr. Chen, whatever you're comfortable with, and that's okay. Yeah, whatever you're comfortable with, you can use that. I don't like being called just by my last name, so I prefer if you don't call me just like Chen. And then just like a slight pet peeve of mine is just like people who just start emails that just say hello without any kind of like acknowledgement of me as a person here. But anyway, okay, a couple things. The musts and the please. So one, you must read the syllabus, and I think this has already been covered for you in your discussion section if you attended. And if you didn't attend, please, I know the syllabus is really long, but it really kind of lays out all of kind of my policies and what we expect in the class. I also sent out invitations to CampusWire. That's going to be our discussion forum. So please don't create some kind of group me or group chat or some side discussion thing. Put all of your questions on CampusWire. It's going to thread the conversations. So rather than just kind of one long feed of gibberish and whatnot, it will at least organize your questions, and you can answer each other. And I was debating whether I was going to make CampusWire a required thing, participation on CampusWire. I've decided not to do it, but I do hope that you still use it as a resource. Other students will answer, and I can also answer, and the TA can also answer, things like that. You guys are here live, so that's great. But if you can't attend live for whatever reason, you do have to watch the video. And so this is being recorded, and I will post it online. Please do come to office hours. Any kinds of questions and things like that, you will probably get your fastest response and resolution if you come to office hours. I'll straight up admit that I am not great at responding to my emails. You can send me a direct message on CampusWire, and I'll probably respond to that a little bit faster than email. But the fastest will be office hours, and I've got pretty much an hour of office hours every day, Monday through Thursday, as well as Saturdays. So hopefully at least one of those times will work, and you can if you have a question or an issue, it can get resolved quickly. And I'm able to kind of put, if it's a private issue and you want to speak privately, I can put people in the waiting room and things like that, and you can speak to me privately as well. And if you do attend live, I do like it when students turn on their cameras, which many of you have done, and so thank you very much. But again, that's entirely your prerogative. I'm not going to force anybody to turn on their camera there. Okay. So this is, we'll take attendance, but not in the traditional manner. Okay, so so you will have to answer what's called a lecture viewing quiz. And so let me just kind of show you on, let me switch to student role. I think this is what you see on CCLE. So, so on CCLE, oh, there's a download course material. Okay, well, everything's, oh wait. Is this your textbook? I don't know. Okay, I have to talk about the textbook in a moment here. Okay, and I actually don't have slides for it. But in under week one, today is week 1 Tuesday, and there is a lecture viewing quiz. And basically, if you open up the lecture viewing quiz, okay, don't do this right now. You'll see these 3 questions. Okay, and there's no context to the questions. It just says A, B, C, D, E, A, B, C, D, E, A, B, C, D, E, right? There's no way you can answer this, except if you attend the lecture, I will say, during lecture, I will say something like, the first quiz question, the first quiz answer is the letter B as in bear. Okay, and you will jot this down, and that I'm actually giving you the answer right now. So if you have a piece of paper and a pen, write this down and just write number 1 is B. Okay, number 1 is B, and then and you will select this. Okay, and then throughout the rest of the lecture, so over the next, I guess, hour and 42 minutes, I will give you the other 2 answers. Okay, and these are just done at arbitrary times. You just kind of have to be listening a little bit to kind of hear out the answers, and that's how I'm going to kind of enforce that you attend lecture. The quizzes are due before the next lecture begins. So this quiz, so our next lecture is Thursday at 4 o'clock. So this quiz is going to be due, Thursday 3:59 or something. Okay, and then Thursday's lecture, the corresponding quiz will be due, I guess, before Tuesday, the following Tuesday's lecture. Okay, so that's how it's going to go. You're not going to find the answers in the lecture notes. You'll only find them by listening to the lecture. Okay, and treat this like a quiz, in that you can't give the answers to the quiz to a classmate. All right, because that's cheating, right? So anyway, does that make sense as far as how the lecture view quiz is going to work? And so and that's I already forgot what I put in the syllabus, but I think it's worth like 15%, right? And so it should be an easy yeah, it should be an easy 15 percentage points that you get just by basically coming to lecture, or at least watching the lecture, on a schedule, right? And this will also prevent, I don't know if this ever happened, but I know it happened to some students where, you skip a lecture and then you'll say, oh, I'll watch it later. And then you skip the following lecture. And then, come midterm or finals and you're like, oh my gosh, I've got 4 weeks of lecture to watch. And that's just a disaster. Okay. I mean, I love statistics, but I can't do a marathon of statistics lectures. So don't do that to yourself. And so, just by kind of doing these viewing quizzes, that will at least keep you on track. And so anyway, that's how it's going to work. Okay. I think, and then have you guys used Gradescope before? Okay. And if you haven't, it's pretty easy. You take a PDF and you upload it. Okay. And then after you do that, like if there's different questions, you kind of like select your pages and you say, all right, this page corresponds to this question and things like that. For the homework, it's just graded on completion. So you're just going to kind of click all of your pages, and then the grader will just kind of flip through them and say, oh yeah, that looks like you did all your problems, and you'll get your points. Okay, so lecture viewing quizzes. Will the lecture slides be posted? Yes. I am often working on the lecture slides like right until the last minute. And so So they might not get posted until like a few minutes before class begins, but they will be posted. And so you can do that, okay? Let me talk about the textbook. So there's a question, will the link to the textbook be on CCLE? I think so. I'm not quite sure 100% how it works. But this class is part of inclusive access, which means it's a fancy way of saying we're going to force you to buy the, well, not force you, but we're going to give you the textbook materials digitally, and we're going to kind of automatically bill you, right? And if you don't like that, you can opt out, right? But you have to opt out before Friday. If you wait after Friday, the bill is going to show up on your Bruin bill, okay? The textbook is this. Okay, this is what the physical textbook looks like. I don't know why, but the physical textbook is like a bajillion dollars. Let me find it. Shouldn't be, but it is. And I guess, you know, this is the 4th edition. No, I want the 5th edition. Here we go. Yeah, this is crazy talk. Okay. So if you try to buy new, that's 186. On Amazon, you can rent it for 22. And I guess if you order right now, you'll get it by June 24th. And so I don't know how much the cost is via inclusive access. They told me it's much less than 186. I don't know if it's competitive with this. So, you know, it's up to you. You'll need the book to do your homework problems. You'll need the book for, it's around $42. Okay. So that, you know, it's up to you. If you, one convenient thing is, and I guess the e-textbook, okay, so it's comparable to the e-textbook price versus the physical rental. And I'm not quite sure the economics of this and why the e-textbook, which should cost less in terms of distribution, costs more than the hardcover rental and things like that. I'm not quite sure why that's the case. If you would rather rent it, you can do this. You have to opt out. You get it however you want, okay? And if you don't want to support Jeff Bezos, you don't have to go on Amazon. You go on whatever website you want to get it, okay? But again, if you don't do anything, you're going to get the digital version, but you're going to get billed, you know, $40-something, okay? And if you don't want that to happen, you have to opt out, okay? And I want to make sure that this is clear, just so that no one's going to be surprised by, you know, this thing appearing on their Bruin bill. If you pay for the, I don't know how the, what do you call it? DRM works for the digital version. I don't think they will let you download a PDF. You probably have to read it in your browser so that they can verify that you've paid for it and you have an account and things like that. I'm not 100% sure how it works. Okay, so okay. So I don't know where you find the digital textbook. I think there's supposed to be a link on CCLE when you log into CCLE. Is that correct? Does that appear automatically? Does any other student know how to get it? They said it's going to show up. Oh, geez, people are saying it doesn't thing, and it said it should be under the UCLA Store course material, but it's not there. It doesn't show up. Okay. All right, I will have to get back to you on this, okay? Because I don't. Let me talk to the the textbook people to figure out what's going on, because they said it should show up, but yeah, UCLA Store course material, it's supposed to be there. Okay, I'll reach out to them. All right, so I apologize that it's not showing up. Maybe it'll show up. No, it should show up. They said it shows up from day one, which was Monday. So it shouldn't show up after the deadline. It should show up day one. I'll contact the textbook people and figure out what's going on. Okay. Any questions before I get started on Stats 13 exclamation point? Okay.
I have a question with the software R. So we're supposed to download that, correct?
Yes. Yeah, that will all of this stuff. If we have time at the end of today's lecture, I'll talk about that a little bit. That will be covered by your TA in discussion section.
Okay, thank you.
Let me pin my. Oh, what did I do? Okay, I just made my face really huge. Okay. Okay. Slide this. Okay. I love statistics. Heart, heart, heart. Okay. And so this is I really do. And I recognize, I don't think anyone here is a stats major, and that's okay. And I recognize that not everyone is going to love statistics the way I do, and that maybe you're only taking this class because it's required for whatever major you're pursuing, and that's okay. I understand that too. But I do hope that at the end of the course, you will gain an appreciation for the subject, okay? Sometimes, you meet people and then they ask you, hey, what do you do? And you say, oh, I always tell them, I teach. And they say, oh, what do you teach? I say, I teach statistics. And then sometimes people's reactions go, oh, statistics. I hated statistics. And that always kind of hurts my feelings a little bit, because it's, I don't know, someone says like, oh, what do you do? And you go, oh, what, I hated that thing. That's not a nice thing. So anyway, I hope at the end of this course, if somebody ever talks about statistics, you're not going to say, oh, I hated statistics, that they'll be like, oh yeah, that was a good class. That's my dream. I don't know what's going to happen, but okay. But anyway, so why do I love statistics? Well, it helps us make sense of stuff, right? So I say, life is full of variation. Everything and everyone is different. That's just a fact. You are unique. No one else in the world is exactly like you. No one else in the world can replace you. And you are beautiful. So, and I'm not just saying that to whatever boost your ego, but I truly mean it, okay? And the fact that we're all different, right? We can attribute this variation, the fact that everybody's different, to part of it. We can attribute variation to just randomness, right? The DNA that went into kind of the gametes and whatever that formed you is a result of a random process, right? It's like randomly selecting genetic information, from your biological ancestors and things like that. And it created kind of the exact set of chromosomes that define who you are. But then other aspects of variation, right? Variation between people can be attributed to other factors, right? Physical characteristics could be related to nutrition, and personality traits could be related to, relationships or parents or friends or things like that. And this subject of statistics can help us distinguish between what could be due to randomness versus non-random causes. All right, and so here's an example where statistics is really important, right? And this is made up data based on real life stuff, right? So imagine we have this kind of following fictional data, right? So let's say they're trying to develop a vaccine for a disease, okay? And so during phase 3, the phase 3 trials of the vaccine, this is where they're kind of like giving the vaccine to a whole bunch of people, and they kind of want to see how effective it is. Let's say, 21,720 people got the vaccine. And in that group, 60 people became infected. And then we have another group that's of similar size. They get the placebo. And in that group, 82 people became infected. Okay, placebo being this thing that has no kind of known medical effect or anything like that, right? And so we'd say, oh, 60 is less than 82. does that mean that the vaccine offers protection against the disease? Okay, so we say, in the vaccine group, only 60 people got infected. In the placebo group, 82 people got infected. Okay, so there's a difference there. And if this were the data, does the vaccine offer protection? The answer is maybe or maybe not, right? One argument that somebody could make against the vaccine, saying that it doesn't offer protection, would just be to say, you know what, this difference between 60 and 82, it's not that big of a difference, right? And really what could be going on is that that the vaccine offers no protection and that both groups just get infected at the same rate. But because it's a random process, naturally, you might, just out of randomness, you might get more in one group and less in another group. Just like if I told two students to take a coin and flip it 100 times, one student might get 55 heads and another student might get 45 heads, right? Just because it's a random process. Sometimes from randomness, some people end up getting more random outcomes of the coin landing heads, and other students will get more random outcomes or fewer outcomes where the coin lands heads, right? And so somebody could say, you know what, we're just getting a random scenario where 60 people became infected and 82 became infected in the other group. This is just a random fluke, okay? There just happened to be a few more people in the infected group than that. And if you go through the calculations according to statistics and probability, yeah, it's going to turn out that, it could be the result of randomness, okay? Whereas in real life, these are the numbers, these numbers come from the actual Pfizer vaccine phase 3 trials during the, for the Pfizer vaccine, out of 21,720 people who got the vaccine, only 8 people became infected. And in the placebo group, 162 people became infected, okay? And this difference between 8 and 162 is kind of so dramatic that it would be unreasonable for someone to say, oh yeah, this is just a result of random chance, right? If I gave a coin to two students and I said, flip the coin, and somebody says, oh, you know what, I got heads 3 times, and the other student said, I got heads 50 times or something, okay? You would just say, oh, that's just weird randomness. You'd say, to the student who flipped the coin and got 3 heads, you'd say, you did something weird with your coin flipping, and that's why you only got 3 heads. We can't explain the outcome of getting the coin landing heads 3 times with just, and treat that as if it were random flips, okay? So the difference here, 8 to 162, this is so dramatic that, we can come to the conclusion that the Pfizer vaccine does offer protection against infection, okay? And so, this is this dramatic difference. The previous one, you had a much smaller difference, and there's going to be a lot of results that are somewhere in between, okay? Maybe there's a difference, but maybe not as dramatic as this. And in those cases, we want to still be able to distinguish between what was random and what actually happens, right? We want to be able to make sense out of the data, right? We don't want to just be completely blind, and that's what statistics is all about, okay? And I guess this was actually kind of a question that I had always had growing up. I mean, I don't know, like ever since like high school when we did like science experiments, I was just like, is this really what's going on? And I felt like statistics answered that question and allowed me to kind of start to understand data. And so this is why I truly love the subject here. And so what is this course all about, right? You guys are here. I only get to teach you guys for 6 weeks, and I'm going to try to pack a lot of content in here. We're going to get through almost the entire textbook here, okay? And so there's a lot of stuff going on, but hopefully we can kind of break it up into a way, that makes sense here, right? And so these are, I would say, the most important ideas of the course, all right? And so, for your homework, for your quizzes, for the final exams, you need to know the details on how to conduct these actual things. You need to know how to do figure out the standard deviation and how to do a t-test and how to do one-way ANOVA and things like that. 10 years from now, if you haven't encountered any statistics and you're in some kind of other occupation or things like that, my feelings will not be hurt if you forget all of the details of doing a t-test or confidence interval or things like that, okay? But my feelings will be a little bit hurt if you forget some of these kind of key ideas of statistics. And so if there's anything I want you to kind of remember 10 years from now about what statistics is all about, these are the key ideas, okay? Number one is that we can make conclusions from observed data, all right? That's really what the subject is all about. We're trying to take data and we want to make conclusions from it. And the way we are going to make conclusions, or the reason why is we want to make conclusions about a large population that we cannot directly observe. The idea is you gather data, you're observing kind of a sample of data, and I'll talk about exactly what that is. And based on your sample of data, we were trying to, again, generalize to the larger population. We can't directly observe the larger population. And so we're going to try to make conclusions about that based on a sample, okay? And this is, these are kind of the big ideas, is that if you do observe some association in between variables in the data, okay, in your sample of data, that could mean that there's an association between the same variables in the population, right? You observe some kind of phenomenon in the sample, like you looked at you studied 100 people and you observed some kind of phenomenon here. And that could mean that this is a phenomenon that exists in the larger population, okay? But there's also the possibility that whatever you observed here in your small sample, this is just a weird random thing that happened in your small sample. And so we're going to take some time learning probability. Probability is going to teach us about randomness. And by understanding how randomness works, we're going to be able to decide if the data could be a result of randomness or not. Okay, and that's why probability and statistics often go hand in hand. Classes are often titled, this is your course on probability and statistics. And that's because in order to do statistics, you need to understand randomness, and probability is really all about randomness. Okay. And then the bulk of our course is going to be learning the statistical tools like the confidence interval, like the hypothesis tests, and things like that. And we're going to spend a lot of lectures covering a bunch of these different statistical tools and methods. But again, like a lot of things, if you don't quite use them actively, you'll forget them, but at least you'll have gained a familiarity with them. And if you realize, oh, you know what, this is a tool I might need to use, you can always pull up a reference textbook, and hopefully that will just kind of refresh things in your memory, and you can go from there, right? And basically those tools, they're going to produce numeric values, and those numeric values help us to make some conclusions, okay? This is kind of a small little diagram of where our course is headed. Today we're covering chapters 1 and 2, which kind of cover these big picture concepts, as well as descriptive statistics, how we summarize our data. Okay, and a lot of times people hear statistics and they just think descriptive statistics. It's all about, how do you summarize, a basketball player's games. Okay, and that's an important aspect of statistics, but that's not everything. Okay, there's a lot more. That's only just the first 2 chapters. Okay, and then the next lecture, so Thursday's lecture, we're going to get into probability, and then the following week we'll look at probability distributions and sampling distributions and things like that, where we're going to kind of look at the likelihood of events, the likelihood of not just events but actual numeric values, and then we'll look at the kind of the likelihood or probability of entire samples of data. Okay, and once we understand that, then we can kind of combine our knowledge of descriptive statistics and sampling distributions to perform statistical inference, which is all about making conclusions about the population based on a sample of data. And from there, you've got all of the other chapters 7, 8, 9, 10, 11, 12, and those are going to cover a whole bunch of different statistical tests, right? So things you might have heard of: confidence intervals, t-tests, non-parametric statistics like the Wilcoxon test, the chi-squared tests, ANOVA, correlation, and linear regression. Those are all going to be topics that that we'll spend a lecture on and things like that. Okay, so that's where we're headed. Any questions? We're all good. Okay. Okay. Chapter 1, basic. Oh, it should have been like basic concepts or something. And now I just feel like I'm insulting you or something. Okay. All right. So let's talk about big idea number 1. Okay. So we want to make conclusions from observed data, right? So that was big idea 1. So the subject of statistics is all about making conclusions from observed data. And I'd say, right now we are living in the golden age of data, right? Everything we do is generating so much data. The flip side of that is we're probably living in the dark age of privacy. And I don't know if it's going to get better or worse. I think we're starting to recognize, what, privacy is a good thing. But then again, people are willing to trade it away for convenience and a couple dollars. I don't know, you say, oh, we'll give you a free t-shirt for your privacy. And people will say, okay, that sounds like a good deal for me. But anyway, companies in every sector, whether it's tech, finance, government, health, whatever, entertainment, they're spending tons and tons of money to get data, right? You sit and watch TV, you stream something on Netflix, right? Every little click, every time you just kind of hover on a preview and you let it play, they're collecting data, and they're like, ooh, this little advertisement, they stuck around and they watched the preview. They didn't commit, they didn't click okay to actually play the series. I mean, not that I know from experience or anything, but just this kind of, right? They're collecting the data and they're trying to say like, oh, you know what? These are what's recommended for you. That's why they allow for multiple profiles. And people, they said, oh, multiple profiles, then I can share my account, right? And they're trading away dollars for their privacy for dollars, because what they really want to do is they want to just build up a profile and figure out exactly, are we going to make some movie about zombies and I don't know, whatever they just did. Okay. And so they're gathering data, right? You use your phone, it's generating so much data and it's being collected and harvested. And, there's a big battle between Apple and Facebook and all of these different companies about who's going to do stuff. Okay. So every field of science and research is involves gathering and analyzing data. And why are all these companies so obsessed with data, and why are researchers so obsessed with data is because it's been shown time and time again that when you use data to help make your conclusions, those conclusions are often more reliable than decisions just based on gut feelings, tradition, and intuition. Okay. Okay, so I see a discussion about a textbook being found, and that's fine. I'm going to ask that you don't share the textbook link on Campus Wire, okay? And that's because I don't want to get in trouble with the publishers about like promoting stuff, all right? And I'll just, I'll look away for the moment here, okay? So anyway, that's why, so we can make conclusions that we make based on data are often more reliable than decisions based on gut feelings, tradition, intuition, and things like that. I think people are starting to also recognize that on the flip side, if we give all the control to algorithms, then the algorithms will, because you don't have humans making some of these decisions, they can make bad decisions too. And so I think people are starting to recognize there needs to be a little bit of balance between just handing everything over to AI and algorithms and having people involved. Interesting stuff going on there. Okay. And the second big idea here is, we want to make conclusions about the population. So anytime we're doing research, there is a question that we want to answer. All right, so a couple examples of these questions might be, some experimental drug ABC effective at treating some disease XYZ, okay? Or, if we increase the cost of some product by 5%, how many people will still buy it, right? Like Disneyland, I think if you ever go to Disneyland, like they've been increasing the cost of their tickets for admission. And that's because there's people studying that say, hey, we can increase the price and people will still buy it. And that's all based on statistics and data, right? Not that these are great things, but just that's what a lot of companies, effectively a lot of companies are driven by profits, and these are the questions they have, right? Sometimes we have questions about votes, right? What proportion of voters have a favorable opinion about some politician, right? John Q. Public, whatever. You have approval ratings and things like that. All of these questions, the real answer is based on some associated population. The population would be everyone who would be relevant to answering the question. So if we're talking about treating disease XYZ, the population is everyone who has disease XYZ. If we're talking about, who's going to buy this product, the population is all potential customers of the product, okay? And if we're talking about, people who have favorable opinions of the politician, the population is everyone who could vote for or against the population. Those are the populations. But in all of these cases, or really in any case, when you're talking about the population is too big, okay? Or it's impractical, too big or impractical to kind of observe and study directly, okay? Once every 10 years, the United States conducts a census, and it's a very expensive endeavor, and that's just to try to count how many people live in the United States, okay? And it's very difficult, and you can't count. It's never 100% accurate because some people deliberately avoid, being counted by the government, and some people just, are in a certain living situation where it's difficult to identify these people. And so, just the fact of just trying to count everybody is a difficult thing to do, and much less, survey them for some kind of questions or things like that. The populations are just too big for us to study directly. So what we do, the solution is we will select a sample and we study the sample. And so a sample is a selection of people or subjects, whatever it is you're studying, that's taken from the population, okay? And what we want ideally is that the sample is representative of the population. We want a small group that's representative of the larger population. Once you have your sample, the researcher is going to kind of study the sample, identify information about it, and this forms your observed data, okay? And based on the data from your sample, we're going to try to make conclusions about the population, right? So you have this small thing that represents the larger thing, or hopefully represents, and that's what we want to do, okay? So again, just this kind of example here is that, maybe we're interested to see, is some experimental drug ABC, is it going to be effective at treating the disease XYZ, right? The population would be everybody who has some disease XYZ, okay? And there's no way we could even track down everybody with this disease, right? We might not even know who has the disease, right? Some people who have the disease might not even be aware of it. And even if we did know who has the disease, we can't possibly get every single person to volunteer to participate in our study and things like that. So there's no way for us to study this population directly, the entire population directly. So instead, what we have to do is we have to work with a sample of volunteers. Okay, so we have to say, we're interested in possible new treatment for this thing. If you sign up, we'll give you some money for volunteering and things like that. And we hope that the sample of volunteers you have is going to be representative, or at least similar to the general population, right? And so, you know, this is often very difficult to pull off in real life. Generally, your sample of volunteers will be limited to your local population, right? So you might be a researcher working in a hospital or near, you know, with ties to a hospital. And so all of your volunteers will be kind of living within, you know, a 30-mile, 50-mile radius of your location. It's very difficult to get, you know, volunteers internationally unless you have some large coordinated effort. And so you're just hoping that your local population is kind of similar to, you know, a larger population, and it might be, it might not be, right? So, you know, you might find studies conducted in the United States, and the studies conducted in the United States, you know, we've got to use caution if we want to generalize to, you know, a population in Europe or a population in Asia or something like that. And conversely, if there's a study conducted in Asia, you know, it might not generalize to the United States because the sample may or may not look like the larger population. Okay, so anyway, you gather data from your sample, and maybe in when you do your analysis on the local data that you have, you find that people who took the experimental drug recovered from the disease at a higher rate than those who didn't. All right, and so that's hopeful, right? You go, oh, the experimental drug, that's improving at a better rate than the traditional treatment, and so that could support the idea that the experimental drug is effective at treating the disease in the population. Okay, but we also have to explore the possibility that the results in our data was just a result of randomness, right? And that's really what the rest of this course is all about. Okay, we're just kind of establishing some of these key ideas here. So how do we get a sample of individuals from the population, right? That's the sampling process. What we want is a sample that's representative of the population. And if your sample is not representative, then we'll say your sample is biased, okay? So for example, you could end up with a biased sample simply by selecting too many or too few from a particular racial group, or, you know, too many or too few from a gender, or, you know, whatever kind of group of people group you can think of. If your sample, you know, overrepresents or underrepresents that, then your sample could be biased, okay? And that's often an issue for a lot of kind of like AI and machine learning algorithms and things like that that exist, that, you know, the kind of the data that they were using to kind of figure out these models and the AI and things like that, those samples of data, you know, were biased, perhaps not out of malicious intent, but just, you know, the researchers, you know, just they didn't bother to think about these things, and you can end up with biased samples, and issues can result from that. Okay. One method that should produce a representative sample is called simple random sampling. Okay, it's not guaranteed to produce a representative sample, but there's no reason why it should. It's not in the long run. It should produce representative samples. Okay, but again, it's a random process. So because it's random, you might get too many or too few from a certain group, right? And so the way simple random sampling, or SRS, works is we start off with a sampling frame. The sampling frame in the ideal scenario is going to be a list of all the individuals, every single person in the population, okay? And this part, establishing the sampling frame, is often the most difficult task in simple random sampling, and is often generally the source of a lot of bias, right? And so the United States conducted a census last year, and that could come close to getting all the individuals in the population. But the problem with that is that census is already outdated. It's already, a year and a half old or whatever by now. And we haven't even gotten the results because they're still kind of tabulating and counting things out. And so that's already outdated. People have been born, people have died since the census was taken. And so using that as a sampling frame is not going to be perfect. Even if you had something of a limited scope, you just say, all right, you know what, we want to get a random sample of people who live in Los Angeles, in the city of Los Angeles. That's almost an impossible task, just because, is there a single list of every single person in LA? That does not exist. Okay. We might, maybe we work for a government agency and we have access to government records, right? You say, okay, let's go to the DMV and let's find everybody who has a certain zip code, right? But chances are people have moved and their records with the DMV aren't current, okay? Especially among college students, sometimes you live in Westwood, sometimes you live at home, and it's not like every single time you move, maybe some of you contact the DMV and update your address, but I imagine this is not the case for many of you. And so, even using someplace like the DMV or, whatever records exist, and a lot of people don't have permanent addresses, it's difficult to get this, right? And so if your sampling frame is biased, then your sample is also going to be biased. But we're going to just kind of, we're going to pretend for now that we've got a good sampling frame. And once you have that, it's called simple random sampling because all we do is we just select individuals one at a time at random from the sampling frame. It's a simple process, and that's how it goes, right? So, a result of the simple random sampling process is that every individual in the population has an equal chance of being selected. And then every single possible sample has an equal chance of being selected, right? And so that's a strange phrasing there, but one example would be lotto numbers. So lottery numbers, is a example of simple random sampling. There's often some kind of tank with little ping pong balls bouncing around, and every single one of those ping pong balls has an equal chance of being selected. And that means getting the exact combination of 1, 2, 3, 4, 5, 6 has the equal probability of the exact combination of 9, 12, 23, 31, 47, 52. Okay. These exact combinations have both the same exact probability. It seems strange, but there's no reason why this would have a higher probability or lower probability than some other exact combination. Okay. So that's simple random sampling. All right, is that okay? Let me go ahead and give you your second viewing quiz answer. Your second viewing quiz answer is the letter C. The letter C as in cat. The letter C as in cat. So go ahead and jot that down. All right, let's talk about gathering data, okay? We have different sources of data, okay? And so we have anecdotes, we have observational studies, we have controlled experiments. And so I want to talk a little bit about anecdotal evidence, okay? Anecdotes are basically stories about one's experience. These are going to include, someone's story, also customer reviews, also testimonials, things like that. Anecdotes can be useful, all right? And I'm not saying anecdotal evidence is bad. It can be useful, right? So you have Amazon reviews, you have Yelp, you have eyewitness testimony, and court proceedings and things like that. But the problem with anecdotal evidence is that we don't have any kind of statistical method that's really able to work with anecdotal evidence, just because as far as Amazon reviews, it's all kind of self-selected who leaves a review, and you often kind of get this situation where people leave a bunch of 5-star reviews, and or people will leave 1-star reviews, and that's kind of what you also see on Yelp and things like that. If somebody just had kind of a mediocre experience, they often don't have much to say, right? If everything met expectations but wasn't like super amazing, they'll often just kind of leave it as that and don't have much to say. Amazon, a lot of these sites also have issues with, kind of people leaving fake reviews and, groups review bombing things and stuff like that. So there's all kinds of issues. Testimonials and stories, for example, somebody says, my aunt, whatever, purchased these essential oils and it helped her, whatever pain and things like that. And it cured these problems. And I'm not denying that this was the experience of a person, but it's also difficult to say that this individual's experience is necessarily going to be universal for other people, right? Yeah, in the comments it says some sites allow for the user to gain points to leave reviews. Yeah, and very often, if you download an app, you'll get like, oh, please leave a review and unlock some benefit or something like that, right? And this, there's a lot of questionable tactics and things like that, right? And of course, every video you watch on YouTube, they're like, comment, and subscribe, and whatever. They're just trying to bump up their numbers, right? So anyway, individual experiences are just going to vary greatly, and we can't use them to just make conclusions about the general population. And so, better than the anecdotal evidence, we have observational studies. Okay, and so observational studies, usually we have to organize and come up with some way to gather data and things like that. And the general idea here is that we're observing. Okay, we're observing the subjects that we're studying, whether they're people or animals or plants or whatever it is. We're observing these things. Okay, and ideally, what we want is that the sample that we're studying is going to be representative of the population, right? We use random sampling if we can. We try not to interfere with the subjects other than taking the measurements. And the subject's own kind of actions or other things are going to determine whether they are in the kind of treatment group or the control group. So, perhaps we're interested if, what effect does a daily exercise regimen have on, some other aspect of health or something like that. And if it's an observational study, we're not going to force people to start exercising. We're just going to kind of observe people. And some people exercise and some people don't. And that's it. That's the person's own actions that kind of determine whether they're in the exercise group or the no exercise group, right? And so at the end of the study, you might find some kind of association. There might be a relationship that's uncovered in your study between variables, okay? But despite finding an association or some kind of relationship, we're not going to be allowed to make a conclusion that one variable is causing changes in the other variable, okay? And so, just to kind of illustrate this, I have this silly example, is that we could study, do a broad study across different households in the United States. And perhaps one of the things that we'll look at is, the reading performance of the children. So, do you have children in school? And we say, are you reading at grade level, above grade level, below grade level, things like that, okay? And we also just count how many electronic devices belong in the home or exist in the home. And electronic devices being things like phones and iPads and TVs and, whatever Alexa devices and things like that. We're gonna count all of these things up, and what a study like this would reveal is that it's not going to be a very strong relationship, but there will be a relationship in that generally households with a lot more electronic devices might have children who have higher reading performance than households with fewer electronic devices, okay? And so is the answer to say, oh, if we want to improve reading performance across the country, we just have to give more electronic devices to people. Okay, and that would be a silly conclusion. Okay, or the opposite and silly would be to say, oh, when students are able to read better, they buy more electronic devices. That's also a silly conclusion, right? And so what's really going on? Well, the answer is a lot more complicated, but probably points to a lot of kind of social inequity and injustice and things like that. And that there's kind of been this long known phenomenon that households with higher income tend to have students with higher reading performance at school. And the answer is not just that the money suddenly makes people better readers, but perhaps money gives access to better educational resources. Maybe perhaps if a household has more money, then the parents don't have to work multiple jobs, and the parents are able to kind of spend more time to kind of develop these things at home, reading skills at home and things like that. And it's the issues, as far as why, is a lot more complicated. And statistics is not going to be able to answer these things. It's all we can do in this subject is just kind of point out that this relationship exists, and yeah, the relationship exists. As to why or what's causing it, that's a lot more difficult to answer, right? And so in a lot of these situations, some kind of confounding variable is another variable that can end up explaining the association. And even that confounding variable, like income level or something, perhaps will not fully explain everything, right? There's a lot of things that are a lot more complicated and involved in that. Okay. We also have controlled experiments. In a controlled experiment, the subjects are assigned to be either in the treatment group or the control group by the researcher. Okay, the researchers assign who gets to be in the treatment group and who gets to be in the control group. The subjects don't get to choose that for themselves. Okay, and so in these cases, ideally, the sample size that you're studying is large enough to observe a range of outcomes. You want to see people who have one result and people who have a different result and things like that. The researchers should be using random assignment to put people whether in the treatment group or control group. And because you've done the random assignment, there shouldn't be a reason why the treatment group is drastically different from the control group. Okay. Participants in the study should be blind or blinded whether they are in the treatment group or the control group. They shouldn't know, I got the actual medication or I got the placebo or something like that, right? In some situations, the researchers have to make evaluations, right? So for example, perhaps you want to know if a medication is effective at treating depression, okay? Depression and anxiety. And depression and anxiety is something that is not measurable from in a physical manner, right? Like if we wanted to know if something affected weight gain, we can just say stand on the scale and we get an answer right away, right? Does something affect depression? That's a lot more complicated, and you have to kind of have some kind of evaluation. A person has to ask you questions, and you have an interview, and they're going to say, okay, your depression has improved, your depression has gotten worse, things like that, right? And so if the person who's making the evaluation also, they need to be kept blind. They can't be like, oh, this person got the medication, and therefore, because that could affect the type of evaluation that they make, right? And again, placebos are a tool that's used to kind of help keep everybody unknown to which group that they're in, right? And so anyway, at the end of the experiment, if you find a difference between the two groups, right, because of random assignment, we say, there's no reason why the treatment group should have more improvement or the control group should have more improvement other than the fact that this got the treatment, this got the medication, and this got the placebo. That's really the only appreciable difference between the two groups. Everything else is just kind of randomized. We can say that, the group that did get the treatment, their depression numbers improved, right? Their depression scores got better. And the people who, were in the placebo group, it didn't make much of a difference, right? Their numbers didn't change. And we can say, the only real difference between these two groups was that this got the actual medication and this got the placebo. And therefore, that difference can be attributed to the medication or to the treatment versus control. Okay. So we are able to say that the difference results from which group someone is assigned to. All right, is that okay? The differentiation between the observational study and the controlled experiment, and why we're able to kind of make these cause and effect conclusions from the controlled experiment, but not from the observational study. All right. Okay, I hope so. Okay, let's get into chapter 2. For our lectures, I've got a lot of stuff to cover, so I'm gonna go. I go straight 2 hours. Okay, I'm gonna just be talking the whole time. If ever you need to just take a break and walk away, get a drink of water, use the restroom, feel free to do that. Don't, if you have your camera off, I don't even know if you're still there, right? You might just have the computer on in the corner of the room. Sometimes that happens. I suspect it's happened a few times because sometimes the class has ended and there'll be a student who's just kind of still logged in. And I'll be like, hello, are you there? And there's no response. And I'm like, oh, maybe they fell asleep. I don't know. Okay, but anyway, let's talk about describing our data. We've got variables and things like that, right? Okay, so variables. Once you have a selected sample, we record information about individuals. All right. Every piece of information we record is a variable, right? And they're called variables because they vary from person to person. And we have, 2 types of variables that we're going to really concern ourselves with in this class. We've got numeric variables. Numeric variables describe a quantity, like how much or how many. Numeric variables often have units, not always, but often. Okay. Categorical variables, on the other hand, tell us what type or what kind. You might find more differentiations. You might have like ordinal categorical variables and nominal categorical variables. And for numeric variables, they have like interval and, different types of absolute things. And we're just going to broadly cover them as numeric versus categorical. Okay. And so, when you gather your data, you're often going to arrange it in some kind of table with rows and columns. And generally, what we want is each observation to be its own row. And each row is going to have only one observation in it. And if you have some sample size, the sample size, we use the letter N, N for the number, which is our sample size. That's going to be the same as the number of rows in our table. Okay. Every column you have is going to be a variable. Every variable is its column. Okay. And each column contains only one variable. So, for example, we could gather some information about students or people, and we might have Alice, who is age 20, is female, has a height of 62 inches, has brown hair, and has area code 310. Brett is age 19, male, 71 inches tall, black hair, area code 562, and things like that. Okay, so which variables are numeric and which ones are categorical? I think we can look at this and easily identify them. And perhaps the one thing that might throw us off a little bit is that the area code is categorical, but I will just go ahead and do this, right? So the name is maybe our identifier, but we can also just treat it as a categorical variable, okay? The age is a numeric variable. It tells us how much and, or how many times has somebody gone around the sun and things like that, how much time has somebody been alive. And it makes sense to make comparisons. We can say Alice is, about 1 year older than Brett, okay? As far as gender goes, this will be categorical. As far as this data goes, we have female and male represented here, okay? Height is numeric, and we can make a comparison, 62 inches versus 71 inches. We can say Brett is taller than Alice. As far as hair color, we have brown hair and black hair, and there's going to be different colors of hair. That would be categorical. And then area code, these look like numbers, okay? They are numbers, but the numbers don't represent a quantity. They don't represent how much or how many. And so this is actually a categorical variable. And one question you can ask yourself is, does it make sense to say, there's more of this than that, right? So it doesn't make sense to say Brett has more area code than Alice, right? Brett has what, 252 more area code than Alice? That's a nonsense statement, right? It makes sense to say Brett is 9 inches taller than Alice, but it doesn't make sense to say Brett has more area code than Alice, and to have kind of like the average area code, that doesn't make sense either. And so in that case, it doesn't represent a quantity, so it's going to be a categorical variable here. Okay. Let me talk a little bit more about categorical data. Okay. So most of the time, we're going to record categorical data with some kind of description of the category, right? So for example, if we're talking about hair color, we can say there's brown hair and black hair, blonde hair, red hair, maybe other colored hair and things like that. Maybe white hair or something like that. And, other colored hair, if somebody has colored their hair, purple or something, we can do that, right? Sometimes we might end up coding the categorical variables with numbers, right? So for example, we could take this, and rather than writing down the word brown hair, we could say, people with brown hair is getting recorded as category 1. People with black hair gets recorded as category 2. Blonde hair gets recorded as category 3, et cetera, okay? If you do this, it's important to remember that these numbers, 1, 2, 3, don't represent numbers, but they represent categories, right? And so they no longer have that numeric meaning. It doesn't make sense to say hair category 3 is more than hair category 1. And it also doesn't make sense to try to take an average of these hair category numbers, okay? On the other hand, it's also possible to turn a numeric variable into a categorical one, right? So for example, you could take age, which we often treat numerically, but we could turn them into categories, right? We could say you have minors and adults. Minors would be anyone 0 through 17, and adults would be anyone 18 or higher, at least in the United States, okay? I also just kind of want to say this about categorical variables, especially in the context of kind of historical data sets and things like that. In our course, we're going to encounter lots of different data sets in our labs and in your textbook exercises. And for some of these data sets, they were gathered years ago, generations ago, things like that, right? A lot of these data sets, gender is just treated as a binary variable, as male or female. In other data sets, they might talk about race or ethnicity, but they might only consider a few races, right? And in fact, in some kind of papers you might encounter, especially if you're looking at older ones and things like that, race might be treated as just kind of a white versus a non-white category or something like that. And so, a lot of these data sets that you might encounter will often fail to represent all groups of people, right? Especially groups that are marginalized, especially groups that are not being considered. And sometimes this is because of just the researcher's ignorance, reflecting kind of attitudes of the time. Other times it could be due to just blatant biases and prejudices of the researchers, right? And definitely that has existed in past studies. And so it's healthy to look at any kind of data set, even data sets that are collected today with this kind of critical perspective, and say, are we leaving out entire groups of people and stuff like that, right? Even in those cases, flawed data sets can still be useful. You can still make some conclusions from them, but it's also it's important, I think, to consider the limitations, of the conclusions that you can make, especially if they're, completely ignoring or leaving out groups of people and things like that. It's important to just be mindful and say, what, we can't just generalize to all people, but we can only generalize to, whatever groups of people that were even considered in the first place in this study. Okay. All right, let's get back to just kind of some of the tools that we have as far as summarizing, say, categorical data. Okay, so here we have a frequency table for a categorical variable. Okay, so here I guess we went to I don't know, field of flowers or something. I don't know. They had 182 poinsettias, okay? And I did not know this until I saw this textbook example, but you know, you can get poinsettias in a bunch of different colors. I've only seen like red ones around Christmas time, but you can get red poinsettias, pink poinsettias, and white ones. And apparently in this study, we had a total of 182 of them, okay? And we can summarize the different categories and say, you know, we encountered red 108 times, pink 34 times, and white 40 times. This is what we call a frequency table, okay? It summarizes the categorical variable. So even though you've got numbers here, it's important to remember that the underlying variable is categorical. It's telling us what is the color of the flower, red, pink, or white, okay? And so if you looked at kind of the raw data, we would have, you know, 182, that would be our n, okay? We can represent the categorical, this frequency table using what we call a bar plot or bar chart, bar graph, whatever we have. And basically you just have a bar with the height of the number, okay? So you have red has a height of 108, pink has a height of 34, white has a height of 40, and this is our bar plot, okay? The arrangement of bars in a bar plot is completely arbitrary, okay? This is arranged red, pink, and white, okay? It would be just as valid if we wanted to go pink, white, red, okay? Or if you arranged them in any other order, right? So later on, we'll be talking about the shape of distributions, okay? But the shape of distributions only applies to numeric variables because here I could, quote, change the shape by just rearranging the bars, okay? And so if we can just arbitrarily change the bars around and manipulate the shape, there's really no shape that applies for a categorical variable, okay? So we'll talk about shapes of distributions later or in just a moment here, but there's no shape of a distribution when we're talking about a categorical variable. Okay, so, oh, not green check, I guess whatever. Okay, so here I've got just made up scenarios here. Okay, so let's say we had this data set where we have red, pink, and white, 60, 61, 61, and we have this data set, red, pink, white, 140, 40, and 2, all right? And so the question is, which graph, the one on the left or the one on the right, shows more variation in colors? Which one has more variation in the color, all right? And so if you think it's the one on the left, oh yeah, under reactions, you can do green check, and under reactions, you can also do red X, right? You can do red X or green check. Does that, you guys see that under Zoom? Okay, all right, so why don't we just think about this and maybe on the count of 5. Okay, or somebody's already doing this. Okay, but just go down on 1, 2, 3, we'll count to 5 and then just go ahead and give us your reaction and we'll see who we get, okay? All right, so ready? 1, 2, 3, 4, 5. All right, show us your reactions. Oh, look at this. It's pretty split. We've got 24, 30 versus 28. Some think the left one on the left has more variation. Others think the right. So I think it got up to like 37 versus 26 or something like that. Somebody gave us the confetti flag or the confetti popper thing, whatever this thing is, the celebration. Okay, so what do we think? It's kind of split. The one that has more variation in colors is going to be the one on the left, okay? The one on the left. So I want you to think of this. The way you can kind of picture this, just imagine closing your eyes and standing in this field, and then imagine closing your eyes and standing in this field, right? So if you go over to the one field on the right and you close your eyes and you say, oh, you know, you wake up and you go, oh, where am I? Oh, what am I surrounded by? You're just surrounded by red flowers. It's like red flowers everywhere, a few pink flowers and hardly any white flowers. We would say there's not a lot of variation as far as the colors of flowers that you've encountered there, okay? On the other hand, if you close your eyes and you teleport to this field over here and you open them and you look around, what do you see? you see a big mix of red, pink, and white flowers. And as far as a categorical variable goes, you're going to get maximum variation when all of the categories are equally represented, okay? When one category shows up with a much greater frequency, like this one over here, there's less variation. There's less variation. Hang on, how do I clear? I don't know how to get rid of my own reactions on this thing. I'm forever stuck on green check mark. Oh, okay, I made it go away. Yeah, if the question was, is which numbers have more variation? Yes, certainly these numbers have more variation. 140 is very different from 2, whereas 60 and 61 are all very similar. But that wasn't the question. The question was, which one has more variation in colors, which is more variation in the categorical variable, okay? If we were asking which one has more variation, like the height of the bars, yeah, certainly the one on the right, the heights of the bars are different heights, but that wasn't the question. Is that okay? I hope that clears that up. Okay, let's talk about numeric variables now, okay? So here is a data set. And this data set, this comes from our textbook, okay? This is just the raw data. We have, I guess, 36 men, and they measured serum, I think this is creatine phosphokinase, and it's measured in microliters per liter, or something, I don't know, whatever, some concentration, okay, in their bloodstream. And these are the numbers that they got, right? 121, 82, 100, 151. We have numbers for 36 people. DeLauren, are you raising your hand with a question? Oh, okay. No problem. So, okay, we can summarize all of this data with another kind of frequency table, all right? So, I mean, this is also a frequency table, except we don't have categories of, right? It's not like we have categories red, pink, and white, but what we're gonna do is we're basically going to kind of categorize or bin them into little groups here. And so we're going to create a bin going from 20 up to 40. So the square bracket on the left means starting at 20 and including 20, going up to, but not including 40. So this would be like 20 to 39.9, okay? And then this next one with square bracket 40 goes starting at 40, going up to, but not including 60. So like 40 to 59.9, things like that. And we can go through and we can kind of start counting these up. And so we say, well, how many numbers are between 20 and 40? I've got one person with a number of 25, and that's this one person here. How many people have values between 40 up to, but not including 60? Okay, we have 4 people. This person 58, 57, 48, 42. Those are the 4 people here. How many people have values between 60 and up to, but not including 80? And there are these 7 people. We have the 68, the 64, the 60, the 78, 62, 67, 70. Okay, and so there's 7 people there. And you can go through and do this for all 36 people. And you would create a frequency table that looks like this. Okay, so this is our frequency table. And once you have this frequency table, then you can make a visual representation of this, okay? And this is what we call a histogram, right? So it looks a lot like the bar chart, okay? So you have bars with the height showing basically the number that showed up in the frequency table. So between 20 and 40, this bar has a height of 1. From 40 to 60, this bar has a height of 4. From 60 to 80, this bar has a height of 7, and so on and so forth. So bar of 8, things like that, okay? One thing you'll note, as far as the aesthetics of this bar chart and this bar chart back here, just aesthetically, we often put little gaps between the bars when we do categorical variables, and when you have a numeric variable We often don't. That's an aesthetic choice. What's important here, though, is that the arrangement of bars is not arbitrary. The arrangement of bars is tied to the number line, right? So this bar that has a height of 1 is always going to be to the left of the bar that has a height of 4, because this one, you know, it's from 20 to 40, and the next bar goes from 40 to 60. And I'm not allowed to just say, you know, I want to rearrange the numbers and I want the number 40 to come, you know, before the number 20 or something like that. So we can't rearrange the bars. They're tied to the number line. And so now we can start talking about, you know, what is the shape of the bars that get formed here, right? So what is the resulting shape here? Okay. Before I get into that, though, there's another graphic display that we might call, or that we call a dot plot, okay? And so you can take numeric data. So here we had, you know, what is this? The serum CK values. But here we're looking at, I guess, piglets born to different sows on I'm assuming some kind of pig farm. And so here, these are the different numbers. And so, you know, is it a litter of pigs? I don't know what's a group of pigs called. I grew up in the city, so I know nothing about animal husbandry, but here, but apparently, I guess a lot of piglets are born at the same time. And so here we said, you know, how many, the number of surviving piglets of 36 different sows. We have, you know, for one sow, 5 piglets survived. For another sow, or 2 sows, 7 piglets survived. We had 9 sows where 10 piglets survived, and, you know, so on and so forth. We had 2 sows where 14 piglets survived, and things like that. And so we could represent all of these data. We can take each data point and represent it with a dot, okay? And so here, this is a dot plot. Every dot represents an observation in our data. And so you have, stacked at the 10, you have 9 dots, each dot representing a different kind of sow and her number of piglets. And so we have 9 dots here. Next to the 10, we have the 11, and there are 8 dots in this column at 11, and things like that, okay? Now, this works if you have something like 36 observations in your data set. If you had something like 3,000 observations, you would end up having 3,000 dots. And at that point, the dots kind of all merge and blend into like lines and stuff. And so it's not so useful. So dot plots effectively, you know, really only recommended if you only have a few unique values. This dot plot shows the exact same information as this histogram, okay? And so this histogram, if you kind of imagine just drawing lines over this thing here, you would end up getting this exact shape here. And so here we have the exact shape. My preference, I've always liked histograms more than dot plots, but the dot plots do exist in the literature. And so I want to kind of just mention them here. Yeah, sow is a female pig. Yeah, they have all kinds of things, right? So you have a cow is a female bovine only after it has had a child, and before before a female bovine gives birth, it's a heifer. And I don't know, somehow I know this a little bit more about, you know, and you have bulls and steers, and, you know, also, okay, anyway, we don't, this is not about that. Now we're talking about radish seedlings, another favorite subject of mine, I guess. These are just examples I'm taking from the textbook, by the way. So when we look at numeric values, we'll look at a few things. We've got the median, and we have the first and third quartiles, okay? So the median is the 50th percentile. I think you guys are already familiar with this, right? This is the spot where half of the data is less than this, and half of the data is going to be greater than or equal to the median. So if you are at the median, then, you know, if your height is median height, you know, half of people that you encounter in general will be shorter than you, and half of people you encounter will be taller than you, and things like that, right? And then you also have Q1 and Q3, the first quartile and the third quartile. So Q1 is the 25th percentile. So that means 25% is equal to or less than Q1, and Q3 is the 75th percentile. 75% is equal to or less than Q3. We often hear about Q1 and Q3, you know, I don't know if you guys were worried about this when you were applying to colleges and you had your SAT or ACT exams and you were looking at, you know, this school, their 25th percentile and 75th percentile for these exam scores were in this range, and you look at your scores and you're like, okay, I feel like I have a good shot to, I don't know. Okay, but that's often where people encounter 25th and 75th percentiles. You don't see them published very often in too many other spots here. But okay, let's just take a look at this data set here. We're looking at, I guess, radish seedlings grown in total darkness, and we have radish seedlings grown in constant light, okay? So generally, when you plant something outdoors, you have a daytime and you have nighttime, and we're just curious, what if we just left the lights on all the time? How much did these seedlings grow? And we measured them. And these are the numbers. And the first thing we got to do is we got to put them in order, right? So that was kind of a step 0 that we didn't show here, okay? But with 14 of these, the median is going to be halfway in this halfway spot where we're going to have 7 values below the median, 7 values above the median, okay? So you've got the median is going to be something like 9.5. Halfway between 9 and 10. Okay, and then once you have this median, the median, you just basically look at this lower half. We got 7 numbers. And so what's the halfway point of the 7 numbers? That's going to be your first quartile. That's going to be 7. Okay, you look at these numbers on the right. They're in order. You take these 7 numbers. What's the halfway point of these 7 numbers on the right? That's going to be Q3. That's the third quartile, Q3. Okay. Technically, there's other methods as far as calculating the location of Q1 and Q3. When we use R, R employs a slightly different method for calculating the quartiles. So you'll often get very similar but slightly different numbers. You know, if you're going to calculate the quartiles manually, this probably is the easiest. Split it in half and then split each half in half again, and you basically get quarters, right? So that's what we're going to do, right? Okay, so I guess I just did it out loud, but here I have this slide that kind of explains all of this, right? So we have 14 numbers, so half of them are below the median, 7 numbers below, 7 numbers above, and we're going to find basically the mean of the 2 central numbers, 9 and 10, right? If you have an odd number of values, like we do for 3, 5, 5, 7, 7, 8, 9, if you take these lower half of values, we have 7 numbers here. We would find the middle value, which is just going to be 7, the median of these 7 values, which is 7. The median of these 7 values is 10. Okay. I think that's okay with you guys, right? All right, so we have a graphic display that goes right along with numeric summaries, or with the median Q1 and Q3. And that's called a box plot, okay? And so a box plot, you're going to start by drawing a box, okay? So here's my number line. The edges of the box are going to be Q1 and Q3, which is 7 and 10. And then we draw a little vertical line at the median, okay? So this is going to be the start of my box here. So this is what I get. I get 7, 10, and a vertical line at the median, 9.5. Okay. And then what we do with the box plot is we're going to extend lines from the box, and these are called whiskers, okay? So sometimes we call the box and whisker plot. And the lines will extend to the smallest value and the largest value in your data set as long as they are not outliers, okay? So then now that raises another question. What's an outlier, right? So what's an outlier? So outliers are going to be values that are considered far away from everything else. And in order to decide what is an outlier, we have to find kind of these imaginary boundaries called the lower fence and the upper fence, okay? So the lower fence is the first quartile, Q1 minus 1.5 times the IQR, right? So you imagine taking, this box has a width of 3, 7 to 10, that's known as the IQR, okay? The IQR is basically the width of the box or the difference between Q1 and Q3. So the IQR is Q3 minus Q1, we do 10 minus 7. That's the width of the box. That's our IQR. And basically, we're going to go 1.5 times the width of the box below Q1. So we're going to take this width of 3, and I'm going to go down 1.5 times that, 4.5 down to here. And I'm going to take this width of 3, this box, and I'm going to go 1.5 boxes up from 10. So the lower fence is going to be ends up being 7 minus 4.5. I get a lower fence at 2.5. I do the same thing on the high side. And so the edge of the box here is at 10. And I add 1.5 times the IQR. So I add 4.5 there. And this takes me up to 14.5. So this is my lower fence and upper fence. Okay. Is it always 1.5? As far as this class goes, yes. We're always going to go 1.5 times the IQR. There are different, opinions about how to determine outliers. I'm just showing you kind of like the basic ways of getting your quartiles and the basic ways of figuring out where your upper and lower fences are for outliers. Yeah, as you get more into statistics, you're going to find, there's this person's method and that person's method, and they all end up kind of giving very similar results with very, nuanced and subtle distinctions. I think this is a straightforward and simple way. So yeah, as far as this class goes, we're going to go 1.5 times the IQR down, 1.5 times the IQR up from Q1 and Q3. All right. And now we're going to figure out what's the smallest point and largest values in our data that are not considered outliers, so within the fences. And then everything outside of the fences would be considered outliers. Okay. So our data, all of the values are 3, 5, 5, 7, et cetera, going up to 14, 20, and 21. Okay. So the smallest value that we have that's not an outlier is 3. And so we're going to draw a whisker from the box down to 3. And then the largest value in our data that is not an outlier is 14. So we're going to go from the box up to 14, and we draw a whisker there, right? Okay, these values, 20 and 21, are part of our data set, and they're going to be considered outliers, okay? And so we're going to represent them with dots or circles. And this is our box plot, okay? Generally, you don't, when you draw a box plot, you're not going to write the location of the upper fence or lower fence. Usually, these are just invisible. And oftentimes, you won't even bother writing 7 or 10. Questions, so we round them? Round what is your question? So the whiskers, the number, so if my data was 10, 10, 10, 12, 20, and 21, okay, the largest number I have that would not be considered an outlier would be 12. And so my box plot whisker would end at the 12. Okay, and you have a little gap from there to there. Okay, so so here there was no rounding of numbers. My raw data numbers were just these numbers 3, 5, 5, 7, 7. And so, if you had some number like 14.2, you would take it out to 14.2. Okay, if the number was 14.7, 14.7 would technically be above the upper fence, and then it would be considered an outlier. I don't know if I'm answering your question. Okay, the question: are we going to need a TI Inspire or a specific calculator? No, you don't need a TI Inspire. Okay, where did I put my calculator? I just like I like a simple scientific calculator. If you have a graphing calculator, that's more than adequate. If you have a scientific calculator, that's also adequate. You basically need to be able to do like decimals and square roots. That's going to be important. I think scientific calculators make it a little bit easier to input your values and things like that. Where did I put my calculator? Okay, this is the calculator I like. This is a Casio FX 115. I don't even know if they make it anymore. They have something, a slightly upgraded version of this thing. I think it's around $15. Let me just check here. We'll go. Oh man, it's not carried anymore. Okay, well, I searched for something. All right, and I got this thing. This is kind of like my calculator. It's 18 bucks. I think that's a reasonable price. But again, if you already have a scientific calculator, no need to buy another one, right? If you got a graphing calculator, no need to buy another one. If your calculator looks like this, okay, you might consider upgrading, right? If you only have plus, minus, multiply, and divide, yeah, although this does have a square root, you probably want something a little bit better than this, but you know, I mean, technically the exams are open book, and if you want to use your computer, like you can do your calculations on your computer too. Like once you have R, you can, like if you need to, you're allowed to use R, so you can do like square root of 2. Get, you get your number there. so that could work too. So and R is free, so you don't need a fancy thing. Okay. Oh, I didn't put a slide here, but so the thing about box plots have less detail than, say, this histogram. Okay, Desmos. I've never heard of that, but it's a good online calculator apparently. Okay. So the histogram has a lot more detail. The box plot has a lot less detail, okay? But sometimes that's exactly what you want. Sometimes you want less detail. Because if you have to make a bunch of comparisons between a bunch of different groups, too much detail is too hard for your brain to keep track of everything, right? So a box plot, you can just kind of immediately look and go, oh, that's where the median is. And you can just say like, oh, the median is here for this group. The median is higher for this group. It's lower for this other group. You can look at kind of where the lowest value is and where the highest value is. And you can say, oh, you know what? There's, quite a lot more spread between the lowest and the highest value, or there's a lot less spread between the lowest and the highest value. You can say, oh, there's a lot of outliers in this group, or things like that. So box plots really just give you a quick visual summary of some of the key elements of the data without the need for, oh, how many numbers were between 10 and 11, or, things like that. So box plots are great in that way. You can imagine taking our histogram though, and then just drawing some kind of curved line over it. Okay, just some smooth curved out line. And you could end up getting shapes that look something like this, right? So something that looks like this is kind of your normal distribution looking thing. We would say this is symmetric because the left side looks like the right side. And this is bell-shaped. The idea of it being bell-shaped is like you could attach some kind of handle here. And it almost looks kind of like symbols, or you could, I don't know, you could be ringing a bell like this and, holding a thing there, okay? This, I mean, you can imagine a weird looking bell, but this we would say is also symmetric, but not really bell-shaped. This kind of, these tails are like, the edges here are way too long. This thing is skewed to the right, and this one is skewed to the left. This is, we call this the tail. This is kind of the long skinny edge that kind of goes on, it looks kind of like a tail. Or if you had to think of stabbing some, skewering a piece of meat, which side would you use for the skewering? You would use the right side. Over here, you would use the left side. And so that's what we would, to help you remember, skewed to the right and skewed to the left. Okay, what does it mean to be skewed right or skewed left? Okay, and symmetric. Skewed right means kind of most of your values are kind of on the lower end, and you have a few values on the right end, okay? Some extreme values on the high end, the right side tail, and you don't really have any outliers over here. So something like income is skewed to the right, okay? Most people probably make, I don't know, between $0 and $200,000, okay? And that's already a huge range, $0 to $200,000 per year annual income. Okay, but are there people who make $1 million a year, $5 million a year? Yeah, there are. I mean, maybe not a ton, but there are millionaires, people who make millions of dollars per year. And that, if you think of kind of like, if this is 0, and let's say this is 200,000 here, 5 million is 25 times away from 0 from 200,000, right? So you go, if the distance from 0 to 200,000 is this, you take this and you go 25 times, that's going to be the location of 5 million, right? So that's like really far out here. That's going to be very skewed to the right, okay? Skewed to the left is kind of the opposite. Most of the values are on the higher end. Yep. And there are some extreme values on the low end. That would be our left side tail. You don't really have any outliers on the right-hand side, okay? Example there would be maybe scores on a fairly easy exam. So if you think of an exam that, mostly pretty easy, most of your scores might be between like 80 and 100 or something like that, 85 and 100. That might be the bulk of your scores. There still might be a handful of students who score very low, say, so if let's say the median score is 85, okay, the difference between the median and the max score is 15 points, 85 to 100, okay? And then, there could be somebody who scores like a 40%, 85 down to 40%, that's 85 to 40 would be 45 points. That's 3 times the difference from 85 to 100. So that's going to be skewed to the left, okay? Symmetric would mean most values are kind of near the middle, and you approximately have the same number of values that are much greater than you do that are much lower. So a lot of things like human height, most people are kind of average height. You have some people who are really tall, some people who are really short, but most people are kind of in the middle, and you have approximately around the same number of people who are really tall as you do people who are really short. And, whatever your definition of really tall and really short are is going to, depend, but overall height of all humans kind of put together would look symmetric. So, so we've talked about these numeric summaries, and there's one more aspect that we need to talk about as far as summarizing our data, and that's this concept of spread, okay? And we have range and IQR, which we've already seen. So the range being kind of the difference between the smallest and the largest values, and the IQR being the difference between the third quartile and first quartile, basically the interquartile range, the range of the quartiles in the middle. And there's another measure of spread, and that's going to be the standard deviation and the variation, and these measure spread. And so you can imagine, say, 3 rooms of people, and I want you to think about the ages of the people in the room, right? So think of a 2nd grade classroom at the start of the school year. Okay, at the start of the school year, what are the ages of the students in that 2nd grade classroom? Pretty much everyone is age 7, okay? You might have a 6-year-old, you might have an 8-year-old, but by and large, the ages of students in that classroom is going to be 7, okay? So we would say we have low spread in ages. Pretty much the numbers that we're looking at, they're all very similar to each other, and so we have low spread in the ages, right? Okay, let's think about our classroom here, some undergraduate college classroom. We would probably have medium spread in ages, right? So, a lot of students are going to be, somewhere between 18 and 22. But, a lot of students also transferred here and maybe took, a few years in community college, or maybe some students are returning after kind of a break or military service or different kinds of things. And so you're going to have students that are older than that. And so you're going to have a larger spread in ages there, if you think about all of the ages that you might encounter in a college classroom, right? I don't know if anybody's been to the DMV, and probably not recently. You probably wouldn't want to go recently, but at the DMV, you've got all sorts of people, right? You've got teenagers, you've got adults, you have seniors, you have children of adults, people renewing their license, people, getting their driver's test for the first time and stuff like that, you're going to have a high spread in ages, right? You might find a baby that's a few months old. You might find a senior that's 85 years old, 90 years old, and pretty much everybody in between. And so we would say we have a high spread in ages there, right? And so rather than just using these generic descriptors like low, medium, high spread, we can actually quantify the amount of spread that we have, right? We can actually say the amount of spread is 0.2 years, the amount of spread is 3.4 years, the amount of spread is 16.8 years or something like that, okay? And that's going to be how we quantify our spread using the variance and the standard deviation. And so here's kind of the first formula that will show up here is the variance, okay? Don't be intimidated by the formula, or maybe this formula is totally fine with you guys. You can think of the variance as quote unquote the average squared distance from the mean. So we can think of, all right, where are our values and how far are they from the mean? So oh dear, I'm dropping stuff. I'm gonna, with my last couple minutes of time here, let me draw this little diagram. Okay, so anyway, if we look at, if we investigate this formula, we've got the mean being y bar. Okay, so you guys know how to find the mean. You add them up and you divide by how many you have. And each individual value is y sub I. We're going to take each value, subtract its distance from the mean. That's going to be its distance from the mean. We're going to square that. Okay, and we have the squared distance from the mean. And then we're going to add them up and divide by how many we have, except we're not dividing by how many we're going to divide by n minus 1. So that's why I put kind of the average in quotes here, average square distance from the mean. So let me just pull up a little, oops, that's not what I wanted. I want this thing. Okay, let's, all right, so let's say we have 8, 9, 10, 11, and 12. All right, so I've got 5 numbers. Okay, and those will be, let's say ages of children in a family. Okay, all right, and then so the variance s squared is equal to the sum of y sub I minus y bar quantity squared over n minus 1. Okay, so here are my numbers 8, 9, 10, 11, 12. The mean, which is y bar, is going to be 8 plus 9 plus 10 plus 11 plus 12 divided by 5. We're going to get 50 over 5. We get a mean of 10. Okay. All right. And so we're going to say, all right, what is the distance from the mean? Distance from the mean. And it's going to be each value, yi minus y bar. Okay. So if I do 8 minus 10, I get distance in -2, distance in -1, 0, distance from the mean here, minus 10, distance is 1, minus 10, distance is 2. Okay, so these are the distances from the mean, all right? Square distance from the mean, I'm going to take these values and square them. -2 squared is 4, -1 squared is 1, 0 squared is 0, 1 squared is 1, 2 squared is 4. That's a square distance. All right, and so now what is the average squared distance? Okay, what we're going to do is we're going to add these up. 4 plus 1 plus 0 plus 1 plus 4. And it's not exactly the mean. We're not doing the mean square distance. We're going to just add them up and we're going to divide by n minus 1. The reason for that is known as Bessel's correction, and I don't want to get into it. It's not important for this class, okay? But you're just going to do n minus 1. So we're going to add these up. This gives us 10 divided by 5 minus 4, which 5 minus 1, which is 4. And I get a variance of 2.5, okay? The standard deviation is equal to the square root of the variance. So the standard deviation S is going to be the square root of 2.5, which I'll go ahead and use my tiny little calculator. Is 1.581. Okay. And that's how we would go about calculating the standard deviation. I've run out of time to do a kind of another example, but if you took another set of values that were more spread out, you would find that the resulting variance in standard deviation is going to be greater. Okay, well, that is our lecture for today. Let me give you your last view quiz answer. Last third view quiz answer is the letter D. D as in dog. D as in dog. And my recommendation would be to just go ahead and take that view quiz right now before you forget. You need to take it. If you're watching this online or something, you need to complete the view quiz before the next lecture. Okay, that is it for today. We'll end here. Have a good night, and we will see you guys on Thursday. And
Thank you.
thank you.
Thank you.
Thank you, Professor.